Okay, guys, so let's look at this question. Let's look at this question on solid mechanics, aka strength of materials. All right, this particular kind of question. The question here says, analyze the overhanging beam shown here, this one here, figure Q5, this one here on the board, for shear force and bending moments at all critical points. At all critical points. It says, draw the shear force, comma, free body and bending moments diagrams. Determine the location and magnitude of the maximum bending moment. Okay. So first things first, let's look at the question. The first thing you can observe here is that it says analyze the overhanging beam shown, that's this one here, for shear force and bending moments at all critical points. That's the first thing there, at all critical points. The question will now be, where are my critical points? That's the question there. Your critical points basically are where you have your point loads. That's just it. Your critical points are the points where you have your point loads and then the extreme of the beam. That's all. Critical points are the extreme of the beam. That is this point here. This is an extreme one, your left extreme, and then this point here, your right extreme, and then every place you have a point load, which would include this one here, the first support, this one here, your second support, 80 a point load, 100 a point load. What we have here is a UDL. It's not necessarily a critical point. So in essence, I have 1, 2, 3, 4, 5, and 6. I have 6 critical points. Okay, what's next thing that they said? Draw the shear force, comma, free body and bending moments diagram. I'm to draw 3 diagrams there. The first diagram, there's a shear force, which we'll do after making our shear force calculation. We have bending moments diagram, which of course we will also draw after making bending moments diagram calculation. They said free body. How do you draw free body? Free body is simple. All right. In this question, what we are given is almost a free body diagram, literally. Right? If you're here from my previous class, I mentioned something called support systems, where I said there are 2 kinds of support, basically. The first support is when you have something like this. And I said this is called a fixed support. The second kind of support is when you have something of this nature. And I said this is called a roller support. And I know I talked about a third one, something like this. When you have what there? A pinned support. So that means ordinarily in this diagram, they wouldn't have given you this upward force. No. What they would have given you is that at this point here, they'll draw a triangle and put this one here, your fixed support. Then perhaps another triangle here, this second place here, and then put this one here. This will now be your roller support. And I explained what this meant or what they mean in a previous class. I'm not going there. Now, when you have this fixed support and roller support, when you're asked to draw your free body diagram, all you have to do is simple. Depending on the course in question, if the course is strength of materials, which is what we're doing here, to draw free body diagram is very simple. All you have to do is remove this one here and put an arrow going upwards. For this one here, remove this one here, put an arrow going upwards. So what I have here is already a free body diagram. That's it. That's all about free body diagram. All right, that's it. That's for strength. Are you doing applied this semester? Applied next semester. Applied and strength are the same thing. It's just that there's a difference. So when you do applied and strength are the same thing. In applied, you have to draw shear force. You see similar topics. In applied mechanics, the reaction will be different. So in this case here, you have 2. This will give you an upward reaction or a vertical reaction and a horizontal reaction. This is what it gives to you. All right. When we come to the next semester, we'll look at it. So when it comes to what's it called? When it comes to applied mechanics, it's the same concept, just that few changes. Example, the reaction. But in strength, don't bother. Just take upward forces. Now, I am stressing this so that when I say draw a free body diagram, you know that what I have here is already a free body diagram. Now, all you have to do is to come here and then say, after doing this, you now say, label the supports A and B as shown below. You come here and put A, you come here and put B. That's it. I asked some of you that have solved this to send me your work, and I was just smiling. So just come from nowhere. Arrow A is equal to arrow A from where? In your question, were you giving A and B? No. So when you're saying arrow A, you have to define where the A is. All right, so your starting will now be label the supports A and B as shown below. It must not be A and B. It can be P and Q. It can be M and N, but you have to define it there. Somebody just send me their work and I'm just smiling. Just say from nowhere, arrow A from where? Where is your A? So if I were to be like a wicked lecturer now, as you put arrow A, me I'll now use pen and come and put A for you here, and I will circle it. And there's nothing you can do. Literally, nothing you can do. All right. So no hard thing is done. Okay. So I think I've given you the preface. I've showed you the critical points. I've showed you free body diagram. Now let's do shear force, right? So as usual, please get your calculators, please. As usual, my first task here would be to get the value of the reactions at the support, right? To get the reactions at the support. So this is point A. I'll call this, please, A should be here. We'll call this arrow A. This will be point B, this point here, B. We'll call this arrow B. So you can say, let the reactions at the support A and B be arrow A and arrow B respectively. I was telling you, I said, see, if you see my script in exam, it's just so good. Even when I write nonsense, you can't mark me bad. The way the guy arranged the word is just so nice. Right? The question now is this: how many year 2 students would think of writing the way I've just written? Almost everybody know. You just want to copy, that's all. But if you look at my work, the way it's so detailed, you just fall in love with my handwriting. That is the goal. That is the goal. Anyways, all right. So let's get the reactions and the support. To get the value of RA and RB, first thing we have to do is do what there? You say summation of vertical forces equal to 0. So summation of vertical forces equal to 0. I'll explain what this means. All right, so I'll take the sum sigma F force Y vertical will be equal to 0. Then I'll use my sign convention. I would say if it's going upwards, please take it as positive. So we have this. All right. So I have this one here. So summation of vertical forces equal to 0. And if the force is going upward, it should be positive. That's all. All right. With that being said, let's see what we have there. Now from this beam, right, how many forces in total do I have? You have your UDL, it's a force, 1. You have RA, 2. You have 80, 3. You have 100, 4. You have RB, 5. I have 5 different reactions or forces. 1, 2, 3, UDL 4, RB 5. Now, which of them is going upwards? RA is going upwards, becomes positive. It's pointing upwards. So positive RA, I have this. 80 is coming downwards, becomes negative. We said if it's going upward, it should be positive. If it's coming downwards, it becomes negative. So minus 80, of course, in kilonewton. This man is coming downwards, minus 100 in kilonewton. RB is going upwards, becomes positive. It's going upwards. RA. Then finally, you have your UDL. RB, please. RB, please. All right. Finally, you have your UDL coming, it's pointing downwards. If it's pointing downwards, it becomes negative. And we said the task here would be convert your UDL to point load. How do you convert UDL to point load? Simple. Multiply the UDL by the UDL distance. What's the UDL value here? 40 times what is the total distance covered? It's from here to this point. You can see the UDL spans the entire beam. from here to here. That becomes 2 plus 3.5 plus 3 plus 2.5 plus 2. How many? 13. So I have times 13. Equate it to what there? 0. Summation of vertical force is equal to 0. So equate to 0. Right? I think online, on the course, right, on the strength of material course, I have solved question where the UDL is not the entire length. You can have a question where the UDL is not the entire length. You can start here and stop here, and here is just free. How do you solve these questions? They are the course there. All right, let me stay on track so I don't deviate. Let's get this done. This becomes RA. This and this gives you minus 180 plus RB minus, what do you have here, please? 520 is equal to 0. Okay, these two, what do you have here? RA, take this one here, plus RB minus 180 minus 520 gives you minus 700, equate it to 0. So we have this. Move this man over here. We have that RA plus RB is equal to 700. Of course, let's now bring in units. All right, units here is in kilonewton. So in kilonewton, we'll call this equation 1. All right, so we have this. So that's the first tax. All right, upward force positive, coming downwards negative, equate to 0, and we have this. At this juncture, the next thing is that we'll take moments about either A or B. Whichever one you take will give you the correct answer. All right, whichever one you take will be the same answer. So you can choose to take moment about A and then get RB, or you can choose to take moment about B and get RA. But whichever one, you have the same answer at the end of the day. Let's take moment about B. Again, you can still take moment about A. It's the same thing. Taking moments about B. We have that from here. You can write down sum of moment about B equal to 0. Let me save myself. That's in there. Sum of moment. So taking moment about B, then go down. You write sum of moment about B equal to 0. So it becomes sigma moment M about sub B there. It's equal to 0. Sum of moment about B is equal to 0. Next up, you write your sign convention. Sign convention, if it's going clockwise, we're taking clockwise as positive. So I'm having this man here. This is clockwise motion, positive. Okay, this is clockwise. Clockwise should be positive. All right, where does that bring us to? Where does that bring us to? So here's one place where it becomes tasky. People do not know how to take moment about these points here. What do you do? Okay, so taking moment about B, that's this point here. It means all the forces are coming here. Let's start with RA. RA is going this way towards B like this. So this movement like this, is it clockwise or anti-clockwise? It's clockwise. So it becomes clockwise RA. Moment is force times distance. So the clockwise motion like this is RA to this point. That's clockwise. Please, what's the distance from RA to B? What's the distance? 2.5 plus 3 plus 3.5. What do you have there? 9. Okay. So force times distance, that's all. All right. Positive because it's clockwise. The force times distance from RA to B. We are done with RA. So 1 is check. Next up, 80 is coming downward. I said to trace it, just go downwards like this towards here. So the motion is just come down, trace it down. So down like this. this motion like this, clockwise or anti-clockwise? So anti-clockwise. So anti-clockwise becomes negative. What's the force there? The force is 80. Now multiply what is the distance from 80 to B? From here to here. What's the distance? From here becomes 3.0 plus 3.5. That gives you 6.5. Okay. So I've done RE, I've done 80. Let's go to 100. 100. 100 is come. Just follow the direction. 100 is coming downwards to this point to be like this. This motion here, clockwise, anti-clockwise, anti-clockwise, it becomes negative. So it becomes negative. That becomes minus. So I'm having minus. The force there is 100. Please, this stands from 100 kilonewton to B. What's the distance there? So I have 3.5. Okay. So far, so we have gotten 1, 2, 3, 3. I've done that. Next one will be RB. I've said whenever the force is at that point, don't bother about it to give you 0. Right? So for RB, I would not bother about RB because RB is at point B. It will give me 0. Why? Moment is force times distance. The force is RB. Yes. What's the distance? RB is at that point. It doesn't have a distance. If RB was at the extreme here, we will say the distance from RB to B is 2 meters. If I bring RB somewhere here, that becomes half the distance. So distance from RB to B would have been 1 meter. But now RB is at the exact point, that spot there. So what's the distance there? 0. So don't bother about it. So what do you do next? Here is where it becomes tricky. How many forces did I have there? I have 1, 2, 3, 4, and 5. Yes. So far, so good. How many have I worked with? I've worked with 1, 2, and 3. I was supposed to pick this one as 4, but I've told you why we're not picking this. It's gone. What's last in there? This one here. That's my 5th one. But this one here, whenever the support here is at this point, it becomes tricky. There's how you pick, or there's how you take the moment. For this one here, we'll divide this UDL into 2 parts here. So from this part here, look at this place. This is B. I'll take B up like this. If I take B up, I have a distance from here to here. I also have a distance from here to here. In taking moment about B, this is how we do it. You don't just say 40 times distance. No. We'll consider 40 from the left end and from the right end of B. That's where it becomes tricky. So please watch this. First things first, let's start from the left end of B. So I'm taking 40 and from here to here, the left end of it. From the left end, that's this side here, it is going from the left, from this left here, this part here, towards B. That's like this. What I have here, is it clockwise or is it anti-clockwise? So it becomes what there? Negative. So this one from the left end is anti-clockwise, becomes minus. Moment is force times distance. How do you get the force? To get the force of a UDL, multiply the UDL 40 times the UDL distance. Please, we are working with the left end. So the left end from here to here, what is the total distance? 3.5 plus 3 plus 2.5 plus 2. What do you have there? 11. So 40 times 11. By doing 40 times 11, I have converted the UDL to a point load. Moment is force times distance. What I have here is just the force. What will be the distance? We say UDL acts at what there? Half of what there? Total length. So distance becomes half, 1 over 2, times the total length from where to where? The left end from here to here, which we said is 11. So with this, I've taken the left end moment of the UDL. Now switch over to the right end. For the right end, I now have only from here to here, whose distance is just 2 meters. Where is the UDL pointing? It is pointing downward. So from this point, trace downward towards B. That's the thing there. If I trace downward towards B, this motion here, like this, is it clockwise or anti-clockwise? Please take your time. You're tracing, UDL is pointing downward, all right? You're down the left end. Focus on the right end. So UDL is coming downward. So downwards like this towards B. What you have here, clockwise or anti-clockwise? It's clockwise. Clockwise. Clockwise becomes what there? Positive. It becomes plus. First things first, you want to convert the UDL, that same UDL, you want to convert it to a point load. How do you do that? Multiply the UDL by the UDL distance, which in this case is 2. So it becomes 40 times 2. With this, I have converted the UDL to a point load. Then distance becomes half of that length, 1 over 2 times the distance, which is 2. All right, so with this, I have taken moment about B. So the concept now is simple. For UDL, I'm taking moment from left end separately and then right end separately. That is the idea there. Okay, so equate to 0. So please help me punch, 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 punch. This gives you 9 RA minus, what do you have here, please? 520. Okay. Minus, what do you have here? 350 minus all of this. What do you have here? Minus, give me all of this. I am trusting your answers, please. Sorry? No, like just call it 2220 what? 2420. No point? No, okay. Plus, give me this one here, everything here. So 40 times 2 times half of 2. That should be 18, all right? Plus 80 is equal to 0. Please, this 422420 is 40 times 11 times half times 11. You have this answer. This is year 2, so I won't stress that much. From here, I have 9 RA. Give me this minus 520 minus 350 minus 2420 plus 80. What do you have? Minus what? Minus 2170. This minus 520 minus 350 minus this plus this. What do you have? Minus 3210. So all of this gives you this is equal to 20. Please be careful. From here I have 9 RA is equal to, move this man over here, you have 3210. To get RA, divide by 9, divide by 9. This cancels this. So you have the RA. Please give me 2 decimal places. What do you have? 356 points. All right, 67 units, please. Kilonewton. Please check. It's in KN. Kilonewton. That's it. At this juncture, to get RB, let's put RA into equation 1. Please help me recall equation 1. From equation 1, we said RA plus RB is equal to 700. We had this from equation 1. Now put the value of RA there. RA is 356, please. 356.67. That's RA plus RB is equal to 700. All right, this was a kilonewton, I know, but we are still solving. It's at the final answer that I now put my units. Move this man over here. We have that RB is equal to 700. This man moves over here, becomes minus 356.67. So RB is equal to unit value, please. 343.67. 33 in kilonewton. All right, guys. So at this point, we've gotten the value of the reactions. All right. So RA and RB has been got. I'll put the value of RA just for reference as what is it? 3,356.67 in kilonewton. I'll put the value of RB as 343.33. Let me move this man. RB is equal to 343.33 in kilonewton. All right, guys. So we've gotten the value of RA and RB. So that's the answer, right? So at this point now, we'll now go over to shear force calculation. All right. Now let's do shear force calculation. Shear force calculation. Shear. Let me position it very well. All right, so let's now do shear force calculations. If you look at the question that they said, you should do your shear force calculation and your bending moment calculation at, in quotes, critical points. That was the instruction there, critical points. And I know I showed you where exactly the critical points are. So let's use critical points there. The first one there is at x equal to your first critical point is the beginning of the beam, which is 0. So at x equal to 0, our people will say things like at x equal to 0 meter. Really? 0 meter. It's not like 0 meter or 0 is 0. But people will say at x equal to 0 meter. It's 0, not 0 meter. Uh-huh. So at x equal to 0, please, at this point here, is there any force here? There's no force here. What you're seeing here is just what they used to get this to. As x equal to 0 here, there's no force. There's nothing here. In essence, the shear force is equal to 0. Don't stress. Shear force is equal to 0. There is no force there. At this point, there's no force. Your UDL only starts after here. But at this juncture here, everything is 0. There's no force here. UDL only starts after here. Okay. So my first critical point, x equal to 0, has been settled. What's my second critical point where I have my next point load? I said the extremes and the point load. Where do I have my next point load? At this point here. At this point, what's the value of x here? 2 meters. So at x equal to 2 meters, now, I know I mentioned this when we were doing the shear force class. I said, whenever you have a point load, what do you bring in there? 2 conditions. All right, 2 conditions. One is a point load. So at x equal to 2 meters, I will say 2 conditions. Please. 2 conditions. Condition 1, the shear force is equal to, in quotes, all the forces before that point. So here's my 2 meters here. Before 2 meters here, what are, in quotes, all the forces? All I have here is a UDL. This UDL, is it going upwards or is it coming downwards? The UDL is coming downwards. When the force is coming downwards, it becomes what there? Negative. UDL coming downwards becomes negative. What is the value of the UDL? At this point here, the UDL is just this. And to convert UDL to point load, multiply the UDL by the UDL distance. What's the UDL there? 40. So it's still 40 here. What's the distance here? 2. becomes minus 40 times 2. That's equal to minus 40 times 2 gives you what there? Minus 80. Put in units, kilonewton. Condition number 2, so two conditions. Condition number 2, shear force is equal to all the forces before that point plus the force at that point. Where's the point there? Here. This point here, 2. Before this point, that's all here, we've agreed you had your UDL. Minus 40 times 20. Minus 40 times 2. So it becomes minus 40 times 2. Then add the force at that point. At this point, do you have a force? Yes. Which force is that? RA. RA, is it going upward or is it coming downward? It's going upwards. If it's going upwards, should it be positive or negative? Because what there? Positive. It's going upwards. So take that's what there? Positive. So it becomes plus the force there is RA. Let's put in values. This is equal to, this is minus 80 plus RA is 356.67. Please point for me, what do you have? 276.67 unit kilonewton. I've gotten my second critical point. Let's take the third critical point at x equal to where now? We've taken 0, we've taken 2. My next critical point where I have my point load is now here. At this point, what's the value of x? Here becomes 2 plus 2.5. That's here now. All right, came from here to here. That becomes 2 plus 2.5. So at this point, x is 4.5, of course, in meters. At x equal to 4.5 in meters. So because I said that 0 does not have meter, you're no longer putting meter here too. 2 has meters now. So 2 meters, 4.5 meters, please. Of course, at 4.5 here, you have what there? A point load. That becomes what there? 2 conditions. So I'm having 2 conditions. Condition 1 is simply shear force is equal to all the forces before that point. Let's look at the points there. The point is here, 4.5. Before this point, what force and what force do I have? I have UDL, that's 1. I have RA. So before this point, I have 2 forces. UDL is coming downward, so it becomes what there? Negative. So I'm having negative. What's the UDL there? 40. The UDL is 40. Now, note the point in consideration here. At this point, what is the UDL distance? 4.5. That's 2 plus 2.5. So at this point, the UDL is covering a distance of 4.5. So it becomes 40 times 4.5. This is me converting the UDL to a point load. So I'm done with this. I'm done with the UDL at this point. I'm done with UDL. RA is going what there? Upward. So it becomes positive. So plus RA. Let's impute values. This is equal to, what do you have here, please? Minus 180 minus 180 plus, give me RA is what again there? 356.67. Please do this. What do you have? 176.67 in what there? Kilonewton. These are all the forces before that point. Condition 2, shear force is equal to all the forces before that point. Before this point, what's that point here? We've talked about coming downwards. See, listen. Here is the simple idea. So that I'll save your time. Here is the simple idea. Condition 2 is usually condition 1, then plus this in there. So for condition 2, I'll simply repeat condition 1. That's the concept. Repeat condition 1. I see people at this point, you just say from here, shear force equal to, they will take final answer. That's still okay. But I feel you're jumping a step. All right. So take condition 1 first, which is minus 40 times 4.5 plus RA. Repeat condition 1 first. All right. Some persons, like I said, will just pick up this value because they've already solved this. Just pick up this value and bring it here. That's, if you want that, that's okay. Okay. So before that point, we have this, and then plus the force at that point. This is the point in constitution now. At this point, do you have a force there? Yes. What's the value there? 80. Going up or coming down? Coming down. Positive or negative? Negative. It becomes negative of 80. So minus 80. And that gives you minus, this is 180, minus 180 plus RA is 356.67, then minus 80. So minus 80. Please give me value. Sorry? 96.67 in what there? Kilonewton. All right, so I have this. So this is at 4.5. I've gotten my next point here. What's my next point here? Here. Here is my next critical point. That's at x equal to, will this contain? I don't think so. So let me clean up, please. I don't think here will contain. So let me clean up. All right, so we're done with this point here. The next point is now here. All right, that is at x equal to, at this point, what's the value of x? Here it's 2 plus 2.5, 4.5, 4.5 plus 3, that gives you what there? 7.5. So at x equal to 7.5, don't forget the meters there. At 7.5 here, what do you have here? You have a point load. What does that mean? Two conditions. So two conditions. Condition 1 is that shear force, as we've said, is equal to, except the shear force, all the forces before that point. So let's say this. Here is the point in consideration. Before this point, what are the forces there? You have UDL, you have RA, you have AT. Before this point, RA is going upwards, it becomes positive. 8 is coming downwards, becomes negative. So I'm having RA positive, then negative 80. All right. The next thing we have, before this point, you can see the UDL there. Of course, UDL, as we say, is coming downward, becomes negative. Convert the UDL to a point load. How? Multiply the UDL 40 by the distance it's covering. What distance is it covering? 7.5. So minus 40 times 7.5. You have this. All right, put in the values. This is equal to RA is 356.67 minus 80 minus, what do you have, please? Sorry? 300. 300. Please do this math for me. What do you have? Minus 2.33 units. Please don't forget unit though. Minus 3.33 kilonewton. The number two there is that shear force is equal to all the forces before that point plus the force at that point. Before that point, I just say repeat condition one, which is simply RA minus AT minus 40 times 7.5. Now take the force at that point. At this point, what do I have there? 100. It is coming what there? Downward. So it becomes what there? Negative. It becomes negative 100. If I put in values here, this gives you RA minus 80 minus this one gave us 300, and then this one here minus 100. In total, what do you have there? Minus 123.33 in kilonewton. Please confirm this is correct. Okay. Okay. So that one settled. Let's look at the next critical point. Next critical point here is where I have my next point load. This one is a UDL. We don't consider it as a critical point. So here's my next critical point here. That's at x equal to, all of this you have to do in 30 minutes. At x equal to, at this point, what is the value? At this point, you have 2 plus 2.5, 4.5, 4.5 plus 3, 7.5, 7.5 plus 3.5, 11. So at s equal to 11 meters. Question in my mind, what if I was to solve this in the exam and I'm doing shear force and bending moment diagram? They are now observed that where I was doing bending moment calculation, I had an error. I just observed it there. What would I have done? Honestly, what I would have done is simple. First thing I'll ask myself is there any other question that I know I can attempt very well? I look at the question. Let's just say I was doing this stuff there. Then at bending moment, I now made an error. I just discovered that I've made an error. What would I have done? Simple. The first thing I would do is that I will look at the question there. Is there anyone that I can solve conveniently? If the answer is yes, I will leave that work there. I won't cancel it. Leave it there and start solving the other one that you can solve, because there's no time. All right. Then when I'm done, if I still have time, I will now go back to shear force. I will not cancel that work until I am done with the new shear force. Because what are the odds? If you don't finish, it's better you solve. See, the fact about it is this: if the lecturer sees your work, right, that you're solving is correct, but you made one mistake, he will know that, oh, this guy made this mistake here. But then looking at your work, it will be that you know what you're doing. You just made a mistake. So if the question like this is supposed to be a 20 marks, right? If lecturer is good enough, they could give you like 12 or 15, because they know that you know the thing there. You just made an error. It's possible. So they could give you some. The idea is this: even with that wrong thing, the fact that you're solving is neat and on point, you have some marks. It is better than canceling the whole thing. I will solve. There's no time. You know, even the wrong one you cancel, the new one you did not solve. All right. So that's what I would do. I'll leave it there. Go and do something else. If there's time, I won't cancel that one until I've done the correct one. That's the concept there. All right. So that's something you should keep at the back of your mind. We don't. I would say what you do is that you prepare for the worst. All right. So I was when I woke up this morning, I was saying myself, I was saying, assuming I was going to have exams, I would not be reading for exams. I'll be thinking, what's the worst possible thing that can happen? It's crazy, but that's how I do my things. Right? What's the worst? I enter the hall. What's the worst that can happen? Okay, my pen stopped working. Make I carry 2 or 3 pen. Okay, so I know that even this pen stop, this one will be writing. What else can happen? Do I need a graph sheet? Oh, more circle. The fit here, or I fit the circle. I could get double line. Let me go. So that's how I think. I think in worst case scenario. So if I'm solving and I make a mistake, what should I do? These thoughts. That's what I'm showing you now. So that's how we think in exam. Not that you go and cancel and start resolving it. The one that you can have solved correctly and get full mark, you leave that one and go and kill yourself with shear force. Then village people you can't make mistake two times. You don't like you don't like say in the right exam. Somebody does that. Hey, like when you make the second mistake, you can't help it. You just shout, "Hey!" The exam hall. Like you're like, what's the problem? Oh, sorry, sir, I don't understand. Okay, back to base. Back to base. All right, let's go back to this, please. All right, so at this point here, two conditions. Let's have this. So two conditions. Two conditions. All right, condition one: shear force is equal to all the forces before that point. Here's where we are now. Before this point, what do I have there? I have UDL, I have 100, I have 80, I have RE. Let's keep UDL for the last. RA going upward, positive. 80 coming downwards, negative. 100 coming downwards, negative. So it's positive RA minus 80 minus 100. So I'm having RA minus 80 minus 100. Then, of course, before this point, you have a certain length of UDL. UDL is coming downward, so it's negative. So negative. Convert the UDL to point load. How? Multiply the UDL 40 by the UDL distance. From here to here, the distance is 11 meters. So minus 40 times 11 times 11. So we have this. So you have this. Putting values, this is equal to RA we got as but hold on, no, we didn't at this point I didn't put the value of RA. I just went straight. Okay, but you should have put value of RA first. Yes, yes. So this RA I should just put the value here first. But same thing, no problem, same thing. R is 356.67 minus 80 minus 100 minus what do you have here? 440. Please give me an answer, please. Minus 263.33 in kilonewton. Please add your units. So I have minus 263.33 in kilonewton. That's my value. Condition number two, shear force is equal to repeat condition number one. So I'm going to repeat RA minus 80 minus 100 minus 40 times 11, then plus the force at that point. Here's my point in consideration here. Yeah. At this point, what do you have here? You have RB. RB is going what there? Upwards. So it becomes what there? Positive. So it becomes plus RB. You're having plus RB. So you have this. All right. Let's put in values. R is 356.67 minus 80 minus 100. This value is minus 440 plus RB is what again? 343.33. Please sum this up. What's the value? 80. 80 in kilonewton. So you have this. All right, so we're done with this. Finally, we now have the end. That's here. Finally, we now have the end. That's here. All right, so copy this. I want to clean this part of the board. at x equal to 13 meters. All right, 13 is simply at this point here. That will give you 2 plus 2.5, that's 4.5, plus 3, that's 7.5, plus 3.5, that's 11. 11 plus 2, that's 13. So at x equal to 13 meters, please, at 13 here, please, is there a point load here? So do I need two conditions? Yes or no? At this point, we don't have two conditions. Yes or no? When do we need two conditions? When is a point load? At this point, is there a point load? No, so you don't need two conditions. That's it. Please know what you're doing. Know what you're doing. At this point, please, what you have is not a load. It's just to show what's it called? Distance. That's all. So at this point, there's no point load, so there's no need for two conditions. Go straight and get shear force. So at this point, shear force without two conditions is equal to, it just be all the force before this point. That's all. Before this point, what do you have there? You have arrow A going upward. So you have arrow A. You have 80 coming downwards, 100 coming downwards, both negative, minus 80 minus 100. Okay? You have arrow B going upward. So plus RB. And then finally, you have UDL coming downward. At this point, convert UDL to point load. UDL is coming downward, so it becomes negative. Convert UDL to point load. UDL is 40 times what distance is it covering? The entire beam, which is 13 meters. All right, let's impute values. This is equal to arrow A is 356.67 minus 80 minus 100 plus RB 343.33 minus 40 times 13. What do you have, please? 520. Okay. So please combine all of this. What do you have there? 0. That's a proof that you're on point. I have said this. Shear force will always end with 0. All right? Shear force will always end with 0. Let me ask a question. I've said this before, especially online. I know I did not. Did you share force in person? No, but there are videos online now. So just check my other classes online. I thought chef was there. I said that shear force, I said bending moment will start with 0 and will end with 0. Shear force will end with 0. But the question is this: must shear force start with 0? Yes or no? In your question, in this particular question here, did shear force start with 0? In this question here, the first one we did started with 0. But must it start with 0? The answer is no. Please go and check our previous classes. I've explained that in there. Let me just say on this. Okay, so we are here. Shear force done. Let's do bending moment calculation. All right. Let's do bending moment calculations, plural. All right. So you're doing bending moments at the same intervals you did shear force. That's at 0, at 2 meters, at 4.5. Anyways, bending moment at x equal to 0. Let's start this. As x equal to 0. I have said bending moment will always start with a 0. So do not stress yourself. Moment, bending moment. Moment is force times distance. And the reason why bending moment is starting with a 0 is because I mean, we've literally said at x equal to 0, the distance is 0. So irrespective of the force, at that point, it becomes force times distance. My distance is 0. So anything times 0 gives you what there? 0. Anything times 0 gives you 0. So don't stress. So at s equal to 0, bending moment equal to 0. Don't stress. Don't stress. The next interval we took, please check your shear force, was at x equal to where there? 2 meters. That's what we did next. 2 meters. At x equal to 2 meters, let's do bending moment. You want to take note that the idea of saying two conditions, all the forces before that point plus the force at that point, that only works when you're doing shear force. That idea doesn't work with bending moment. At x equal to 2 meters, here's my point here, this point here. What are the forces before here? You have UDL. UDL is doing what there? Coming downward. So look at this place. I'm simply taking moment about A. That's the concept. You're taking moment about A, which means the force is coming downward. So downwards to this point. So see my motion here. Downward to this point. All right. This one here. Is it clockwise or anti-clockwise? It's anti-clockwise. It becomes what there? Negative. For moment, we want to convert the UDL we have here to a point load. How? Multiply the UDL by the UDL distance. What's the UDL there? 40. What's the distance here? 2. That becomes 40 times 2. With this, I have converted the UDL to a point load. Let's get the distance. This is now the force. What's the distance there? For UDL, it acts at what there? Half the distance. UDL is always half the distance, so it becomes half of the distance, half times 2. So you have this. So we are here now for, listen please, listen. When you're doing UDL, when you're doing bending moment calculation, I'm taking at this point. At this point, so you have what there? RA, but we don't consider it. So listen carefully. If I am doing bending moment calculation, I only consider the forces before that point. The one at that point will not matter. Why? Fine. Let me show you something. Let's just say the force at that point. Let's just assume it matters. If it matters, at this point, what do I have there? RA. RA is going upwards like this. That's clockwise. So plus RA. Please, at 2 meters here, what is the distance of RA? It's 0. Why? RA is at this point. So the distance becomes 0. So it becomes RA times 0. You want to observe that anything times 0 gives you what there? 0. So please listen. When you're doing bending moment calculation, only focus on the forces before that point. That's this one here. The force at that point will give you 0. It doesn't matter. Let's get this one done. This will give you equal to minus 40 times 2 is 80. Half of 2 is 1. Minus 80 times 1 gives you what there? Minus 80. What's the unit? Not kilonewton, no. Unit is force in kilonewton. This one is distance in meters. So it's kilonewton meters, please. The next point is here. Here. This one now. At this point, what's the value of x here? 2 plus 2.5. I said you can make reference to your shear force. We'll still use those distance there. That is at x equal to 4.5 meters. You have this. Let's get bending moment. Bending moment is equal to, again, focus on only the forces before that point. Before this point, what do I have there? I have UDL, I have RA. Here's the point here. RA is going upward, so upward like this to this point. Look at this movement here. That's clockwise or anti-clockwise? It's clockwise, so it becomes positive RA. That's force. Distance from here to here, how many? That becomes 2.5. That man settled. Next up, at this juncture, UDL is coming downward. So it's downward to this point. Please, this movement like this, downward like this, downward here. What you have is called what there? Anti-clockwise. Anti-clockwise becomes negative. Your first task is to convert the UDL to a point load. At this point, to convert UDL to point load, multiply the UDL 40 times the distance is covering, 4.5. So minus because of anti-clockwise, minus 40 times 4.5. With this, I have converted the UDL to a point load. Again, let's get distance. This is the load or the force. Distance becomes half. Don't forget, half of the length. The length in consideration is what there? 4.5. Okay. Again, at this point, we still have 80. But I've said the force at that point will not matter. To give you 0. Don't bother. So let's put in values here. This is equal to RA is 356.67. This into 2.5 minus, please, 40 times 4.5. 180. 180 into 1 over 2 times 4.5. 2.25. All right, so give me final answer, please. This is year 2. Give me final answer, please. Everything there. Final answer. 486.68 kilonewton meter. Please confirm this is correct. Let me know. It's correct. All right. I want to clean this, please. Still writing? Okay. Let's get the next point there. Next point is at x equal to, after 4.5, my next point is here now. This point here, let me put this as x. This point here, from here to here, 2 plus 2.5 plus 3. Use your shear force. We use the next point as 7.5. So it becomes 7.5. You want to add the meters. Okay. Bending moment, it's equal to 7.5 is here. So I'm taking all the forces before this point. Let me start with point load. R is going upward like this to this point. Here's the point here. From here to this point. That's clockwise. So it's positive RA. What is my distance from here to this point? What do I have there? 5.5. So I have RA times 5.5. RA into 5.5. Next up, 8 is coming downward. So trace from downward to this point here. Like this. What do you have there? Anti-clockwise. Look at this. It's from here. Down this way. So this way. Down this way. Down this way. This is anti-clockwise. It becomes negative. 80 times, what's distance here? 3. So minus 8 times 3. Minus 80 times 3. Finally, here, I've taken 1, 2. I have my point, my UDL. Convert UDL to point load. UDL is going down, so down towards this point, down like this towards this point. So it's like this, down this point. This is anti-clockwise. That becomes negative. Now, negative, convert the UDL to point load. It becomes 40 times this distance here, 7.5. So minus 40 times 7.5 minus 40 times 7.5. This is converting, let me use times here. This is converting the UDL to a point load. What is your distance there? Half of the length, 7.5. Again, at 7.5 here, you have this force. It will not matter. I've said that before. To give you 0, it's not matter. All right, this is equal to RA is what? 356.67 into 5.5. We have this minus 80 times 3. What do you have? Times 3, what do you have there? 240. Minus, what do you have for this one here? Everything here. This and this, what do you have? 1125. Please give me final answer. Everything here. Positive 596.69 units. Kilonewton force times distance meters. All right. Next up, at x equal to what next? Here's my next point. Here, this one after 7.5. Here, my next point load. So that's equal to 2 plus 2.5, 4.5 plus 3, 7.5 plus 3.5, 11. So at x equal to 11 of the meters. Voila, we have this. So we can say bending moment Bm is equal to, at 11 meters here, let's take all the forces, let's take moment of all the forces towards the side here. First things first, RA is going upwards. So it's going upwards towards here. That's a clockwise. All right. Upwards towards here. Clockwise. It becomes RA times distance from RA to B, which is simply 2.5 plus 3 plus 3.5. What do you have there? 9. So it's RA times 9. RA times 9. Check. Next up, 80 is going downward. So downward this way to be here. Downward towards here. Downward like this. What you have is an anti-clockwise. So it becomes negative. So minus, what's the force here? 80. From here to here, what's my distance? 6.5. So minus 80 times 6.5. Minus 80 times 6.5. Okay, we've taken this. Next up is 100. 100 is going downward like this. So it's going like this. What you have here, this is coming down this way. Like this is anti-clockwise. Becomes negative. So minus 100 times distance from 100 to this point here. 3.5. Okay. I think I'm done with my point loads. Let's now consider UDL. Like this. UDL is coming downward to this point. Downward to this point. That's an anti-clockwise movement. Anti-clockwise becomes negative. Convert the UDL to a point load. Multiply the UDL 40 by the distance it's covering. 40 times distance here is how many? 11. So minus 40 times 11 minus 40 times 11. With this, you have converted the UDL to a force or a point load. Next up, get the distance, which is what there? Half of the distance. You have this. All right, bring in values. This is equal to RA is 356.67 into 9 minus 80 into 6.5 minus 100 into 3.5 minus all of this. What do you have? 2420. That's all. All right, give me final answer. What do you have here? Minus 7, 9 point. Hold on now. 797. Okay, 0.97. This, okay, kilonewton meter. All right, so I think our last point is now here at the extreme. That is at last point is now here. That is at x equal to 13 meters. That's at this point here. All right, what do we have? Please, I want to clean this, please. Anybody see here? I want to clean this. All right, at 13 here. All right, let's get the forces there. So bending moment Bm will be equal to, the first thing I want to do is to the first thing I want to do here is to, let's start. Okay, before here I have how many forces there? I have 1 RE, 80, 100 RB, and then UDL. RA is going upwards this way towards the very end. That's like this, from here this way. This motion is clockwise, so it becomes positive. So positive of, what's the value here? RA times distance from here to the end, like this. What's the total distance? 11. That becomes RA times 11. 11 is from RA to this point. All right, that's 2.5 plus 3, 5.5 plus 3.5, that's 9 plus 2, 11. So RA is sorted. 8 is coming downwards towards the side here. So downwards towards this, that becomes anti-clockwise. So negative minus, the value is 80. From 80 to this point, what's this sum here? 3 plus 3.5, 6.5 plus 2, 8.5. Becomes 80 times 8.5. Negative anti-clockwise, 80 times 8.5. You have this. Next up, you have 100. 100 coming downward this way. That's an anti-clockwise motion. So minus 100. Distance from 100 to this point, like this. That's 3.5 plus 2, 5.5. Minus 100 times 5.5. Minus 100 into 5.5. And then you have RB. RB is going upwards to this point, upwards like this. So that's a clockwise motion, right? You trace this like this. This is clockwise. So clockwise positive plus RB. Distance from RB to the end here, 2 meters. So times 2. And finally, let's deal with UDL. UDL is coming downwards towards here. That's like this. This motion like this, downwards towards here, is anti-clockwise. So it becomes negative. Convert the UDL to point load, multiply the UDL times, at this point, the total distance is 13. So it becomes negative anti-clockwise. Convert UDL to point load, 40 times 13. Distance becomes half of the length. That becomes half of the length, 13. We have this. All right, this is equal to RA 356.67 into 11 minus just let me just copy this down. 80. Oh, don't worry, give me the answer since you have it. Give me the answer. 6 what? 680 minus what do you have here? 550 plus RB is 343.33 times 2 minus, give me all of this, 3380. This. All right, please give me final answer. What do you have here? Is this zero at the dot or something? 0.02, which is approximately what there? 0. All right, so we are correct. Now, 3.02. Okay, 3, which is approximately 0. You want to note this. Listen, please. You want to note this. Whenever you do your shear force and bend moment diagram questions and your reactions give you decimal points, expect that the bend moment at the end will not be exactly 0. That's the concept here. All right. Reason why we're getting this is because look at the reactions. They are not whole numbers. What I have here is 356.67 and then 0.33, and that's why. Anyways, they've changed the whole syllable. Next semester, you're supposed to do something called numerical analysis. Next semester, you learn this about errors, but I think they've changed your syllabus. Very interesting maths. You learn how to when you do numerical analysis, you start seeing maths in a different light. You see how to manipulate things. Very sweet topic. But that they've changed your syllabus. Next semester, you're now doing eigenvalue, kiniko. Anyways, you're lost. Anyways. All right, so our next task is to get shear force, or to draw the shear force and bending moment diagram. That is after doing our calculation. Now, to do that, all you have to do is to reproduce your beam. And I've said, if in case of exam you're doing this, I expect that, let's say I have my answer sheet and I'm solving this stuff here, and I finish solving at the mid page of my answer sheet. I don't expect that you try to squeeze this diagram in the remaining half, no, of your answer sheet. No, turn to a fresh page and then start from the beginning, draw this at the top and then space it, because you want to space your work. That's the idea. Now, reproduce this diagram again. Then what you have to do is very simple. You can, if you want, you can use short dashes, or you can use straight lines, anyone you choose to. You use short dashes or straight line. Just draw this to the end, right? From each of the critical points, that's the concept there. From each of the critical points, each point you considered, just draw this down. Okay, draw this down. And then draw this down. All right, so you have this. Properly. All right, so you have this stuff. Just draw it down. You could choose to use thin lines, just thin lines. All right, draw this down, and under this you draw both shear force and also bending moment diagram. So that means you're having two diagrams here. So you want to space your work in such a way that it makes sense. I need a list of my points. To help you to know what to do. Please check under shear force. Did we have negative values? For shear force calculation, did we have negative values? We did. Okay, that means shear force will take both up and down. Okay. On that bending moment, did we have negative values? We did. So we have both. So listen. It means that I want to. What I'm saying is this. You don't come here and now say at the middle portion, you now draw this and now draw shear force up and down. Then bending moment that has negative. There's no space for it. So you have to think. Shear force has up positive, down negative. Bending moment also has up and down. So find a way to put a space. Sorry, this board is not long enough, so I'll just have to like manage it. Let me use somewhere around here. Okay, so here's the idea. Please check for shear force value. What is the highest positive value? Just go through them. In your shear force, what is the highest positive value? Go through all of them. What is the highest positive value? 200 what? 27 something. What is the lowest? Go to negative. Minus what? Yes. You have minus 2 something for shear force. So hang on. The highest is plus 27. The lowest is minus 2. Okay, so we have a positive 270 something and negative 260 something, which is they are almost the same thing above and below. Listen now, listen. Get the point here. The highest for shear force is plus 270 something, as I said. The lowest is minus 260 something, which means they're almost the same thing. So when you're drawing pictures in mind, all right, the highest and the lowest. So let's say I'm using here and here, then everything will fall in between. It's a very, very small diagram, but we'll manage it. Then for bending moment, what's the highest positive? Minus 59. Okay, positive is highest is 59 something. The least negative is what's the least value? Minus 80. So that means I have an overwhelming positive and a small negative. Okay. So let's try something. So I could just for I'm thinking about trying to use only here for shear force, then draw another diagram and do bend moments there. Or should I mix them together? In exam, no, you hope you know you mix them together. In exam, you draw them together. That's what I'm saying. So in your exam, you expect to draw shear force here, and this same diagram you should put bending moment under it. That's how it look like in exam. So I'm saying for space sake, should I do it as it will be in the exam, or do I do shear force here? Okay. Yeah, I don't think that's a good talk. You agree? You agree? Okay. Um. Oh, please don't do this. Okay, so I'll have upward. This is for shear force. For bending moment diagram, I'll bring this somewhere around here and see how this works. So this is how it will be in exam. Shear force will be up, bending moment will be down. So let's work with this. For shear force, for shear force, um, please look up, please. Please follow me up. Follow me up. See what I'm doing. Follow me up. Follow me up. See what I'm doing. For shear force at x equal to 0 here, what's the value of shear force? 0. So look at this. This is 0. The datum 0. At x equal to 2, you had two conditions. What's condition 1? Huh? Minus 80. So minus 80. Let me bring it somewhere around here. Please. Minus 80. Then what's condition 2? Positive, Abi. That will go up, Abi. So let me take somewhere around here. 27. That was my highest value, Abi. So let me come somewhere around here. So this is minus 80, Abi. Minus 80. You can come and just put here as minus You don't have to put minus 80. Or okay, minus 80 kilonewton. This is plus what? The 2.67 in kilonewton. That's the value here. Okay, what's the next? The next one was at 4.5. At 4.5, you had two conditions. What was condition one? 17. Okay. What's condition two? So 17 and 96, right? So listen, watch this. Watch this. Please stop and look at what I'm doing here. This is 276. Under this one here, I had two positive answers. The first one was one C. Whenever it's positive, it's upward here. Negative is here. So 17 what? Now listen, 17 will be below this, Abi. If this is 276, 17 will be below this. So I'll take here as that value here. That's 17 what? 667 in kilonewton. Then when you came down, you now had what in? So here is 96.67. 96 96.67 is still positive. All right, so after this point here, the next thing you do is the next point there was 7.5. 7.5, you had to condition. What's condition one? Now hang on, minus what? Now listen, oh, here's minus 80, right? Minus 23 should be what there? It's too small, right? So here's what I'll do. That's why I said you should listen and watch it very well. So what I'll do is I'll just move this one down a bit. And that's why you have to watch your point very well. So I'll just carry this on because I know I'm having, wait, you're having minus 23 and what again there? Okay, so what, listen. This was minus 80. I'll come here. Minus, it was just 80, Abi? So minus 80 in kilonewton. Now at this point, you had minus 2 something. Minus 2. Minus 20 something. 23.33. That would be below this, right? Look at this now. If this is minus 80, 23 should be between here, Abi? So you don't draw it, the idea you don't draw it to be more than this. That's the concept. So let's take something around here. I'll take this part here. It should not pass this one. No, this is 80. So I'll take something around here. This is minus 23.33. Then you bring this down again. Then second condition was minus what there? Minus what? That's more than 80, right? So you bring it down. So if this is 80, I'll bring it down again here. Minus 1, 2, 3. Minus 1, 2, 3.33. Sorry, I'm trying to conserve space. Okay, so I'm here. What's the next point again? What's the next point again? At 11, condition 1, what's the value? So listen, listen. Minus 2 what? Minus 263. So it came down again. Do we have space for bending moments? Please allow me to use it here. Let me use it here. Do we have space for bending moments? Minus 263 point 33. All right. Going up, second condition, condition 2, what do you have there? 80. 80. Look at this is 96. 8 will be less than this, right? 80 should be less than 96. So if this is 96, somewhere lesser than this, 80. Let's use here. This is 80 kilonewton. Then here, what do you have here? 0. Right, so this one, two conditions under 2, you had minus 80 and this. Here, two conditions, you had this and this. Here, two conditions, you had this and this, and then this. So let's trace it. From here, you join from here to here. That will give you something like this. So let me take the minus 80 here. minus 80. I'll join this way. All right. So I have this. Then from here, we had two conditions, minus 80 and 276.67. Take this man upward like this. That's it. At each junction, use an arrowhead. So like this, it means from here to here. From here, condition 2, it's here. So an arrowhead here. From this one, you had this point here. So I'll join this to this, then use an arrowhead. Join this to this. Then use an arrowhead. Okay. From here, this one comes down to this is condition 2. That's 96.67 kilonewton. Comes down here. Use an arrowhead again. An arrowhead. So I have this. Then from here, you now had at this 7.5. Condition 1 was what? Minus 23. Abi? 23 point. So from here, you're moving to this side here, which is from here, you're coming to this side. Okay? Which is arrowhead here. Okay. Then from here, condition 2 was now minus 1 to 3. So come downwards here. At each of the junction, put an arrowhead to show your direction of motion, how you're moving. You're here. After this point here, you now had at 11. For 11, shear force, condition 1 was minus 26 this. So I'm moving from here to here. So you have this. From here, this man goes upward to 80. Condition 2 is 80. Goes up to 80. Then from here, shear force at 13 was 0. So you now have this stuff here. So that's it. At this point, you now shade. If it's below that it becomes negative. So here is negative. Above that positive. Below that negative. Above that positive. You have this. So shading this, shade this. Okay, so you have this. Ta-da! So here you go, shear force diagram. Looks so nice. I miss these days. Kai. So that's your shear force diagram. All right. Let's do bending moment, please. Let's do so copy and let's do bending moment, please. So you want to observe the technicality. By technicality, I mean before I drew this diagram, I didn't just rule and start drawing so that your diagram does not look messy. I first of all pictured in my mind that the highest was 2.7 something, the lowest was this, and then I knew how to position it very well. See the position, it's good. Although I've moved this a bit higher so that bending moment can enter, but then this is still good. Let's do bending moment diagram, please. Please, for bending moment, please check. What is your apex positive value? What's the highest positive value? Sorry? 5.9 something. Okay, what's your lowest negative? Minus, I mean, it's very small, though. Okay, if that's the case, 500 against 80 is literally a no-brainer. It's literally a no-brainer. So, you said minus 80. That's what I was told. Minus 80 something. 80. So here's what I'll do. I'll just bring this one down a bit. It's here. All right, so let's go. Let's go. Bending moment at x equal to 0. What's the value? 0. At x equal to 2. What's bending moment? Minus what? That minus 8 is the lowest value, right? Okay, so look at what I'll do now. Since it's my lowest, I can choose to bring this down, 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 down here. Knowing fully well that nothing goes below this. That's the idea. At x equal to 4.5, the next one, what's the value? Huh? 4, 486. That's positive. So I'm going upwards. 4, let me just use actually, but this is 80, right? And if you get minus 70 minus 80, they are the same thing now. So it's not lesser than this. So it can't go beyond this. It can be close to this. 79 will be close to this, but it's not go below this. Okay, so please, this is what again? The minus plus what again? 7, 4 what? Okay, so I will come here. Let me just put somewhere around. Let's see here. 486. Okay, keep it there. At the next one there, what's the value? That's 7.5. What's the value? Okay, we'll come down here. 5, 9, whatever. The next value here is what? 7, 9 will be, this is 80. 7, 9 will be very close to 80, but not exactly 80. Let me just keep it here. All right. The space here is more than the one here because this is 80, this is 79. This will be a bit, very close, but a bit higher. That's what give you what there? 0. So listen. Bending moment is usually a curve. So when you see that bottom there, you fold as a curve. When you see the top, like watch this. Here's how we do this. So from here, watch you trace this to here, like this. Trace this to here, like this. There's something I will tell you. Before you solve this. We'll do the last part of this solving, which is getting your critical points. Your critical points are your point of inflection, aka point of contraflexion, and then the second critical point is called the position of maximum bending moment. Those are your critical points. Check this particular year, they asked to find in quote the position of the maximum bend. So they didn't ask for two of them, they asked for only one. But the other year may not be just say find the point of inflection. I will show you how to find the two. In case there's any one there, you know what to do. So please watch this. Watch this. Here's what I'm trying to say. Somebody sent me his work and I said there's an error somewhere. Like its work is correct ordinarily, but here's what to note. Listen, you always want to note that your maximum bending moment would occur at the point where shear force is 0. Where does shear force cause 0? Here. Look at this. Shear force cause 0 at here, and here. Right? 1, 2, 3 would give you your maximum and minimum. If you look at it at this point, this is down. Minus 79, minus 80, almost the same thing. Minimum. Your maximum will be at where? So this will be my maximum. In essence, if I'm doing this, I'll just put it here. I'll bear in mind that my maximum will be here. I have this point, but this is not my maximum. Maximum occurs where shear force causes this. So from here, I'll just do this like this. Go up to maximum and then come down here. See what I'm doing here? That's how it's done. There's some of you that sub that sent to me. They move from here to here straight. This is not the maximum. Please. All right. Have this condition in your mind. From here, I'll go down again. So go, sorry. Going down like this. Okay, so see my diagram. Nah, this is just too fine. This is just too fine. So my for my diagram is just too fine. I just feel like I could just like as if I should not clean the body again forever. And it's just too fine. Come on, guys, fine. Okay, minus Upwards, positive, downwards, negative. This negative positive has a meaning, but don't worry about it for now. It's not in your not your level here. Just leave it there. All right, guys. So here's how you will present this in the exam. Shear force on top, then bending moment diagram. So you can come here and put shear force diagram. Shear force. Should you write it? I'm not even sure, sir. You can leave it there. I don't want to spoil this fine work. So leave it there. Right. I don't want to spoil it, please. All right. So just leave it like that. So you can come and write there. Shear force diagram. You should on top. Then here, just find somewhere put bending moment diagram. You should do that. But you're not gonna touch my diagram, please. So with this, we're now left to the final parts, which are find the critical points, guys. Critical points. Okay. All right. All right. So let's do something, please. So at this juncture, normally we should be done, but there's an aftermath of this, which is the last part of this whole thing here, where they'll ask to find any of your salient points. All right. You'll be asked to find critical or salient. It's funny that I've not used the word salient for I've not used this word for over I don't know for over we're looking at 3 years. I've not mentioned the word salient. But when I was doing this, it just came to my mind as salient. I remember why it came to my mind because one of the past questions they now said when I first read the aftermath of this, we're like, look for critical point. And I was like, what's critical point? I had to go and find it. One past question now saying look for salient point. I was like, oh my god. So after critical, now to do salient again. I was like, come on, this is too much now. And I checked. And I saw that salient and critical are like the same thing. I was like, oh, okay. Okay. So it's called critical points or salient points. In your exam, usually, they will ask you for one of them. Please check in this question. What were you asked to find? No, check. What would you ask to find? Location and what? Talk now. What you have to find? Good. You have to find the location and the magnitude of the maximum bending moment. That was the case there. I also show you how to find the point of contraflexion just for all right. There are two critical points for this. The first one is the position of maximum bending moment. Please, BM is bending moment, right? That's what you're asked to find. The position or the location of the maximum bending moment. And how do you find that? You want to observe that the maximum bending moment, as I said, occurs where your shear force is 0. That's it. It occurs where your shear force is 0. And that's what I tried to illustrate here. When I said I use an expert idea to draw this, knowing that the maximum will occur where your shear force is 0. That's how it's done. Okay, so let's get the location and the value. How do you do that? So what you do is very simple. You refer back to your diagram, which is this. So using my eyes, I can see that the maximum will occur here. They can ask for also the minimum bending moment. I've said whether maximum or minimum, it will occur where shear force cuts the x-axis. This shear force cuts x-axis at 1, 2, and 3. Observe that those were the minimum points or maximum points. But since they said maximum, we'll focus on this. Use this idea for minimum. You have the same thing. Of course, here's even easy self. Here, the minimum is what there? 80. Occurs at what there? 2 meters. So the location of the minimum bending moment is 80, is 2 meters That's the location, 2 meters. The value is minus 80 kilonewton meter. That's it. Very easy. This one here. But this one is not very easy because this point here, we don't know the value. So how do you solve it? For this concept here, first things first, I said the maximum bending moment will occur where the shear force cuts the x-axis or is zero. And to solve this, we'll bring up a concept from primary school called similar triangles. How does it work? Here's the thing. All I have to do here is this. I will come here, pick up this part. Look up, please. This thing occurs here. This is where it occurs. I'll come, pick up this part here. I'll bring it out. So pick up this part, bring it out. What do you have there? Here's what I have. First things first, I have this line and this line. So I'll come here, this line and this line. You have, see, you have this line and this line. Then you have this one here. So I have this one here. Sorry. All right, so look at this list. See, this line runs from somewhere here down here. So somewhere here, it runs in my drawing. What's this value here? From here to here, what's the value? How many there? Look at this, 96.67. What's this value? That means this up one here is bigger than the one down. So guess what I'm trying to do? Although it doesn't matter, you can just sketch anything and put the value. But me, it doesn't matter again. It's called a sketch. But let me do what is in my mind. Ouch. Let me do what's in my mind. That guy just shouted, shut up. Felt like he was talking to me. Right? Anyways. Yes, let's proceed. Please let me keep this here. Okay, so 90 here and then 20 here. So I'm just going to join them. So you just do from here to here. Let's see. Okay. Let's take this as here. All right. So this value here is 96.67. 96.67. Now listen. Here is minus 23.33. When representing this here, you don't have to put the minus again. Just call this as 23.33. The minus only shows that it's happening what there? Downwards. Please. Right? Please listen. This is minus 23.33. In doing this here, you don't necessarily have to put minus here. No. Negative only shows that it's below the line. That's all. Okay, so we have this part here. Now, please follow me up, please. From this point to this side, what's the value here? How many? It's 3 meters. I know that from here to here is 3 meters. 3 meters. You have this, and then you have this. So here's what to do. We want to get this distance. From here to here is how many? Listen, if from here to here is 3, from here to here is how many? Do we know this value from here to here? We don't. So we call it what there? X. We call this X. So from here to here, we call this X. Please, if from here to here is 3, and from here to here is X, from here to here what? Becomes 3 minus X. So this distance here becomes 3 minus X. All right, this minus this. That's the thing there. From here, let's get at my triangle. I have my first triangle, this one here, this, and this, and this. Where, please watch this, please. From here to here is 96.67. From here to here is X. That's my first triangle. I have my second triangle here. Like this, and like this. From here to here is 23.33. Meanwhile, from here to here is what there? 3 minus x. So you have this. You try to get that triangle, that's it. See the way I got it. First of all, draw this one out. From here to here is 3. Call here x, call here 3 minus x. So you have this. All right, so here I'll be using similar triangles. Using similar triangles, because of similar triangles is from primary school, literally. It's a primary school concept. So the idea is this. When two triangles are similar, it means their parts are the same. So please watch this. Watch this. So for this, let me call this triangle A and call this triangle B. We'll assume them to be similar. If they are similar, here's my hypotenuse. It means the hypotenuse of A is equal to hypotenuse of B. Okay? This hypotenuse now, please watch this, please. This hypotenuse here, listen, oh, listen. If this is my hypotenuse here, the part below the hypotenuse is what for this one here? X, right? Please watch this. Here's my wood. Okay, let me put this like this. So you see this like this. Okay. Hypotenuse, hypotenuse. Here's the thing. For the hypotenuse there, this side of this triangle, what's the value here? Becomes 96.67 all over below hypotenuse. What do you have there? X. Just equate it to, since they are similar, the sides will be the same. It means this is hypotenuse, this side is 96.67, below this is x. For the hypotenuse here, this side is what there? 23.33, 23.33 all over this side is what there? All right, so this is how you approach this. All right, so look at this, please. So in the layman's concept, the idea is just simply you have these two triangles, you assume them to be similar. That means their sides are similar, and then you equate them. So the simple idea is this. For this one here, the number 96.67, this all over its alphabet, that's x, would be equal to, for this one here, the number is 23.33 all over the one having the alphabet. So it's this. And you equate them. So we have this all over this. At this point here, cross multiply this times this, that gives you 23.33 times x is equal to this times this 96.67 into 3 minus x. Okay, so multiply this. This times x gives you 23.33x. It's equal to this times 3. What do you have here? 290.01. This times minus x gives you minus 96.67x. Let's collect like terms. This one here comes over here, becomes positive 23.33x plus 96.67x. It's equal to this one here, 290.01. So you have this. Please sum this to what do you have here? 120. 120x. It's equal to 290.01. So we have this. So at this juncture, to get x, divide by 120, divide here by 120. This cancels this. X is equal to, what do you have there? 2.417. Give me this in two decimal places. 2.42. X measures a distance, and the distances were in meters. So 2.42 meters. You have this. Now listen, you're asked to find the position of the maximum bending moment. What we have here is not the position. All right. What we have here is just the value of x. And we said x from our diagram was just from here to here. We call this x. We call this 3 minus x. So x is from here to here. 2 point what? 42 in meters. That was this point. We just found this point here. That's our x. So therefore, in the question they said location, right? Location. So therefore, the position or location of the maximum bending moment is equal to, what's the position? You start from any of the ends, either from the left end or the right end. From the left end, what's the distance? From here to here, what's the distance there? So it becomes 2 meters plus, from here to here, how many? 2.5 meters plus, from here to the actual location, how many? 2.42 meters. Please sum this up. What do you have there? 6.92 meters. That is the required answer. So hence, you say the position or location of the maximum bend moment is equal to these meters from where? From the left end, of the beam, of the overhanging beam. That's it. Of the beam. So that's it. They say we should also find the value. Yes. The what? Magnitude, yeah. So let's now get the magnitude of the maximum bending moment. Magnitude of the maximum bending moment. Let's get the magnitude of the maximum bending moment. Let's get that magnitude. How do you get the magnitude? How do you get the magnitude? Look up. How do you get the magnitude? Look up. Here's how to do it. So this is my point here. For me to get the maximum bending moment, its magnitude or its value, all I have to do, magnitude simply means the value. All right. This word is just simply value. The value of the maximum bending moment. Or they can say, what is the maximum bending moment? Same thing. Now to do that, all you have to do is this. We have now known that the maximum bending moment occurs at what value there? 6.92. So from here, trace this back to your beam. Your beam is, let's assume here, leads us straight to about here. And this is 2.42. All you have to do is just to take bending moment about this one here. That's all. Let's give this any alphabet. Any alphabet here. Okay, just say see, all of this is do this. Just say take the moment at x equal to that value there, 6.92 meters. If you do that, what do you have? So look up, please. I'm taking moment about here, right? From here, what are the forces there? RA, number 1, AT, number 2, UDL, number 3. So the 3 forces there. Okay, so let's start with RA. RA is going, see my point, don't forget here. Here. RA is coming this way here. This way here, is it clockwise or anti-clockwise? It's clockwise, it becomes positive. Please, positive from A to this same point. What do you have here? Total distance. That's RA from here to here. How many? 2.5 plus 2.42. That's RA plus times 4.92. You have this. So just take a minute about this. Next up, minus 80. 8 is going this way, downwards towards here. That's anti-clockwise. Becomes negative 80. For 80, distance from 8 to this point, how many there? 2.42. Okay. Are we done? UDL, good. So here, UDL is coming downward. So downward to this point. Downward to this point is negative. So negative. Convert the UDL to point load. That becomes 40. That was my UDL. Times, what's the UDL distance? From here to this point we're considering is 6.92. 6.92. With this, I have converted the UDL to a point load. What will be the distance? Half of 6.92. And that's equal to RA is what? 2 what? Give me RA again. 2, 3 what? 3, 5, 6 points. Sorry, excuse me. 356.67. This is RA into 4.92. Okay. And then we have minus. Please give me 80 and this. What do you have? 193.6. Okay. Minus. Give me this value here. This and this. Just everything here. 957.73 approximately. Give me this one here. Oh, no, just give me final answer. Don't stress it. So look at what I'll do here. Bending moment, BM max. That's it here. Bending moment max. Give me everything here. What do you have? 600.48 units kilonewton meter. All right. When we solve, we never had any value this big. That's why it's called the maximum. You can see there. That's the biggest bending moment value we've had. That's the maximum bending moment. So basically, that's how you answer that question. All right. That's how you answer that question. I said there are two parts, which we've done the first part there, the maximum bending moment. The second one is called the point of inflection or contraflexion. I told you that it's called the point of contraflexion. The other name is inflection. It's called the point of inflection. They are just side by side. Listen. The position of the maximum bending moment is where shear force cuts zero, as I said. That's it. Meanwhile, the point of inflection is where bending moment cuts zero. That's it. Where shear force cuts zero gives you the position of either maximum or minimum bending moment. For point of inflection, we'll look at bending moment. Where does bending moment change sign? For point of inflection, is simply where bending moment cuts zero. That's here and here. So please get the idea. For maximum bending moment, we look at shear force. Where does shear force change sign or cut zero? Here. We use it to solve. For inflection, you leave shear force and come to bending moment. Where does bending moment change sign or cut the x-axis? Is here and here. Usually, in some questions, you have just, listen, in some questions, you have something like this. Look at this. Like this. And at that point, my point of inflection is here. Just simply where bending moment caught zero. In this case, I have two. I have two. How do you get that value? Listen, how do you get that value? Listen, I won't solve this. I'll just explain this. How do you get that value? Simple. All right. To get that value, all you have to do is this. Let's say I want to get the point of inflection here and here, for instance. How do you do it? I won't solve. Just look up. All you have to do is this. As I said, this one is two. So it becomes, the question now be which of them is the real one? Usually it's usually one, but since we have two, let me use this one to explain this. Let's say I'm to find the point of inflection at this point, for instance. Okay, I'll tell you for this, I'll also tell you for this. You get a clearer picture. At this point, all you have to do is that this point where bending moment cuts x, cuts the x-axis, we call this x. That's what you do here. Call this x. Take moment about x. We know that moment about any point is equal to what there? 0. If I take moment about x, what do I have here? I have just this force here. Which force is this? RA. RA. From here to here, aside from RA, which other force do I have there? I have my UDL. So I have UDL and then RA. Question is this. If here to here is x, what is this distance here? Look at this now. If here to here, where it calls this x, if here to here is x, what will be this distance? Huh? Please watch this. Watch this. See, trace this upwards. I'm saying bending moment cuts x-axis here. From here to here is x. What will be this distance here? What would this one be? 2. So what would this one be? From here to here is 2 meters, as you can see. So what would this be? Simply now x minus 2. That's all. So if I take moment about x, it becomes RA is going upwards. You can see here, it's going upwards to this point here. That becomes RA times x minus 2. Now do, what's it called? Do RA into x minus 2. That's this man going upwards to x. For UDL, how would you solve UDL to this point? What would you do? Convert the UDL to point load. That becomes what? The UDL is negative. It's coming down. So negative 40. What's distance there? X. What's it called? What's your distance? X over 2. X over 2. Or half of x, Abi? Yeah, half of x. So who can follow? Equate this to 0. What you have here will be a quadratic equation. Abi? Yes, now. Because look at this. What do you have here? This will give you half into 4 gives you what there? 20. Minus 20 times x gives you what there? Minus 20x squared. Half quadratic equation. Then RA has a value. So RA times x minus. You have a quadratic equation. This quadratic equation equates it to 0. You will solve the quadratic equation. When you solve this, you have a negative term and what there? A positive term. Please try it. Put RA here. You have a quadratic equation. Of course, you don't have to solve it. Use your calculator to solve it. You know how to solve your calculator, right? This is year 2 now. You don't know how to solve quadratic equation using calculator. You should know now. This is how you can solve quadratic equation using calculator. Then when you do that, should I do it? Hold on. Do you guys know what I did here? Okay. What's the value of RA? $356.67 times x. This times minus 2 gives you what there? Minus what? Minus 713.34. This and this gives you minus 20x squared equal to 0. This is quadratic. Please use calculator to solve this. There's a calculator method of solving quadratic equation. I think I've shown this thing before now. So what's your answer when you solve this? X equal to what? X equal to minus what? A is minus 20. B is 356.67. C is minus this. What do you have? Minus 19. Positive 19 points. And then what's the other value? No, it's not possible, sir. Didn't punch correctly. It's not possible. No, 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 no. It cannot x cannot be bigger than the length of the beam. X is from here to here. That cannot be 15 points. This in there. Let me see. Give me a calculator. Let me see. Let me punch myself. Is this quadratic? A is minus 20. B is 356.67. C is minus 713.34. You have 15.53. You have this as 15.53 or 2.29. That's 2.3 actually. Approximately 2.3. That's what you have. So use calculator to solve this. You have these two answers. At this juncture, one answer will not make sense. X is from here to here. So look up, please. Is it possible that S is 15 point something? It's not. So X cannot be this. Hence, this becomes the answer. In essence, the point of contraflexure is 2.3 meters or 2.295, whatever you had there. That's it. You've done for this. Now you come and do the same thing here. Take from here to here as X. Take moment about X. You have quadratic. You solve it. One answer will make sense. One answer will not make sense. The one that makes sense, you take it as your answer. So that's it basically. All right. I have a video where I explain point of contraflexure on my course. So please go and check the course there. You see it. All right. Let me know, please. Any question? I'm done with this. Any question? Most likely in your exam, what you see is just position of maximum bending moment. Right. So kill it and you're done. Yes. Question, please. Yes. If you can plot it on the graph, good. If you use a graph, listen, if you use a graph, it will be much more technical because you have to be accurate. You know, you've gotten your scale 100, 200, so 600 will be like 6 lines, which will take your time. That's why I advise you, if possible, you sketch it. When you sketch, if you sketch, you can do it like this. It's okay. You'll mark it good. So first, you indicate the points there. You'll mark it good if you sketch. But if you use graph, if this is 200, 270, so you have 100, we'll let 1 unit become what there? 100. So 276 becomes 1, 2. Before you get to 3, you now have this. So use your scale to get it properly. That's it. Any other question, please? What's the question, please? This one here? Okay. So, yes, now, yes. If you're talking about this point here, you take from here to be x like this. So if here is x, what's your moment? It becomes RA times what there? From here to here, what will be your value? What will be the value? This is 2 now. This is 2. No, hold on, hang on. I'm thinking about this point, not 9. See the point I'm talking about here. So if from here to here is x and here is 2, from RA, this one here to here, what will it be there? X minus 2. You have RA into x minus 2. That's it. Please watch this. Sorry, my diagram is messed up. But please listen. See, we've done for the first one here. Second one is now here. Where is my second point of contraflexure? Here. This is X. I'll take all the points towards here. What's the first point there? RA. Where is RA? See RA here. This is RA. I'm taking moment about this point. Here's my X. So from here to here is X. What is distance from here to this point? Is what? If look at this, if from here to here is X, look at this. This is X from here to here, and here is 2. What would this be? X minus 2. So it becomes RA into X minus 2. I'm done with RA. What other force do you have there? This one, 80. So from 80, which is this part here, from 80 to here, what will it be? X minus what there? X minus what? 4.5. That's it. So from here to here is X, here to here is 4.5. It becomes, is it minus? Yes. Minus 80 to what there? X minus 4.5. What will the next one be? Minus anti-clockwise 100. For 100, distance from here to here, what will it be? X minus how many? 7.5. That's it. 7.5. That's it basically. All right. So X minus 7.5. That's from here to here. So this is the value of 100. This one here. This point becomes the total X minus this point here, 7.5. For UDL, coming downwards towards here, anti-clockwise becomes negative. Convert UDL to point load. 40 times. What's distance? 40 times X. Because UDL is covering everything here. From here to here, which it actually covers. So 40 times X into what there? Half times X. Half times X. Equate to what there? Equate to 0. So that's it. This will give you another quadratic. So when you solve this will give you another quadratic. When you solve this one here, you would have 2 answers. One will make sense, one will not make sense. CO, put the value of RA here, right? Expand this. You have another quadratic equation. So you don't have negative and one positive, but one will make sense, one will not make sense. And then that's it. Who has finished solving this one here? Anybody? Come on, it can be fast. This is A2, you can be fast with distance. What's the value of RA again? 356.67 times X. This with minus 2. Minus what? 713.34. I'm done with this. This and this minus 80x. This and this plus how many? Plus what there? 360. Okay, that one done. This one is not among. Oh. This one is not among. What do you have here? Minus 100x. This and this plus 750. 750. What do you have here? Minus 20x squared, right? Yes. Half times 40 is 20. X times x is x squared. Please give me the whole numbers. The one without x. This and this and this. What do you have? Without x. This and this and this. What do you have? Minus what? So 396.66. Is there minus to it? There's no minus. Give me the one with x. This one, and this one. What do you have? The ones with x. That's this positive, this negative, this negative. What do you have there? Plus 176.67 what there? X. Then minus 20x squared. We said equal to 0. So equal to 0, equal to 0. This is what do you have here. Just use your calculator shortcut. X is equal to, use a calculator, get us this value. What's the value of X? Sorry? 1.855, or this is in meters, of course, or press equal to again. What do you get? 10.66 what? Approximately 8. 10.689, 69, 869 now, meters, or what wasn't that one point? What did you punch? I get to 1 point something. What are you punching? Minus 1 point, sorry, 86 meters. Of course, it cannot be minus 1 point. Please check. This answer doesn't make sense. You say x is 10, doesn't make sense? Yes, because from here to here is what there? 7 point something. Then plus this one here, 8. So yes, that means the second point of contraflexion is 10.69 meters. So that's it. So if you do contraflexion, take here as x, take moment about x, it will give you quadratic. When you solve, one will make sense, one will not make sense. I have a video where I clearly, this one is kind of rough. I took this man out and I explained how it's done. So please go and check. There's a video there where I explain point of contraflexion very well. All right, so I believe that's about it. Chief, you had a question. Want to end, please? We're not doing video here now. All right, so that's about it, guys. Thank you so much. So, those